So now that we know what the logistic growth kind of model looks like, let's look at the solution to it. So anytime you have something in this form here, dp/dt equals kp c minus p, where c is known as the carrying capacity, which is the most you could possibly have. And if you look back at the first part of this where we talked about how this graph looks, it looks like this. So we have this carrying capacity, which is the max number of people that can, or max population that whatever the system can sustain. K is just a constant. Now, this formula you can see in a lot of different ways. Anytime you see something like dy dt, you can see this a lot of times on the AP exam. Like, think about what this could look like if it was distributed. Like, this could look like a constant times p minus another constant times p squared. Like, this would be logistic growth. Oh, sorry, this wouldn't have to be p. These variables have to match. So whatever the variable is here, these two have to be the same. So this is another way you're going to see these sometimes. So in a lot of the multiple choice, they will write them in a different form. Another form that's kind of common would be dp/dt equals, let's say we take out the c, factor that out. So kcp times 1 minus p over c. So if you see something in this form, and a lot of times they'll take this k times c and just write this as a constant k. So this is another form of logistic growth. And in this case, the carrying capacity is here. Okay? And in this version here, this should not really be c, because that's usually considered the carrying capacity. It would be just some sort of k. Right? If I distribute the k times the c, k times c would just be another constant. So k and d are just straight up constants. C is the carrying capacity if you're writing these, generally taken to be the carrying capacity. So in one of these other forms, you just have to recognize what it is. And I think the best thing to do is try to put it back into the original form. So that's the main thing. Now the book ends up talking a lot about this. So this is the solution to our logistic growth differential equation. If you want to do this, you need something called partial fractions, which will be in not chapter 7, but in chapter 8. So basically you have dp, you put that on the one side, and you put dt on the other, but everything else kind of comes over, kp times c minus p. And partial fractions basically sets things into a over kp plus b over c minus p. And you have to solve for a and b, and then you integrate this up, and you get two ln's on the left-hand side. But for right now, we don't have those skills, those integration skills, so we're going to just say, hey, this is the solution. So later on, when we have integration by partial fractions, it'll actually be, it's not a hard question, but you can do that, as a little example of how to use it. So right now, we have the equation, we have our logistic growth differential equation, and we don't really have to memorize this one here, but we do have to memorize the differential equation for logistic growth. We have to know what belongs where and when it looks like logistic growth. Alright, so let's see how we can use this. So DJ decides he's going to raise sea monkeys. He has a 30-gallon tank, and he starts with 50 sea monkeys. His tank's max sea monkey count is 2,000 sea monkeys. After 1 week, he has 200 sea monkeys, I'm assuming, not just monkeys. Alright, so we want to write a differential equation that models the rate of change of sea monkeys. Now, somewhere in the problem, it should tell you that this is we're going to assume logistic growth. We can't assume exponential growth because, well, your tank can only hold so many. And we have this max sea monkey count, so that's kind of tells me that we're doing logistic growth. So we're going to have dp/dt, so a change in population over a change in time, equals, and we're just going to write this as k times p, and we're not going to know what that k value is now. So actually, after we go and solve all of this, we can come back and figure out what k is, but we need the actual model itself. And then we have our c, which is 2,000 minus p. So as far as writing a differential equation goes, that's what we have so far. Sketch a graph of the slope field. So if we want to do this, we have our slope field, and we know that the maximum it's going to have is 2,000. Now, quick note, don't remember if I said this in the beginning of the thing. The place where my population is going to be growing the fastest is actually always going to be at the half. So at 1,000, my slope field will be changing the fastest. So this is going to look something like this. It's going to be a whole bunch of little S-curves. And you feel free, and these should all be longer. I'm having trouble making my tick marks look right. But we should have a horizontal line here. We should have a horizontal line at the population is 0, and my slope field looks something like so. Okay? And again, the fastest is always going to be at P equals half of the carrying capacity. Alright, let's see, what's our next question? I'm going to just, I think, zoom out a little bit here so I can see more of the problem. So, when will it be growing fastest? So, we already talked about that. That's going to be when it's at half of its carrying capacity. So, now, part that's a little tricky is realizing whether that when is in terms of X or whether it's in terms of Y. So, if we're talking about right now, we'll just say when the population equals 1,000. If you have to figure out what the time is, then we have to solve for the logistic differential equation. So how do we do that? So we have our P of T equals, well, let's take a look up really quick. So what do we know? The P of T equation is our carrying capacity on top, 1 plus d e to the negative kct. Now, negative kct, that really depends on if you know what K and C are. If someone tells you what K and C are, I can just plug those things in. But for the most of the part, you don't usually know that. So 2,000 over 1 plus d e to the, I'm just going to write just K. And you notice how I don't have a negative Kc in here? Because negative Kc is a constant. So I can write that as just a constant K. So what do we know? We have two variables. We have a lot of information. We start with 50 sea monkeys. So at time equals 0, we get 50. So 50 equals 2,000. 2,000, not 200, sorry. Over 1 plus d, which I don't know, e to the 0. So when we solve this, we kind of just rearrange this. E to the 0 kind of cancels out. 1 plus d equals whatever 2,000 divided by 50 is. And so we end up with 200 divided by 5, which is 40. So d equals 39, unless I am brain dead. Want to verify that just really fast. Because if we do have the wrong number, then we are going to be off on the next spot. Okay, so we know that d equals 39, so now this is where we're going to have to come after our k. So we know d, and we know that after 1 week he has 200 monkeys, hopefully sea monkeys. So 200 equals 2,000 over 1 plus d, which we now know is 39, e to the 1k. And your time could be in days, it could be in weeks, it could be in years, but you just have to make sure that whatever it is, it will change your k value. Okay, so we can resolve this thing. So we have 1 plus 39 e to the k equals what, 100? No, 10. It's 2,000 divided by 100. Gets a couple of those. Yes. Okay. So 39 e to the, I think I'm running out of space on my screen here. So we have 9. So e to the k equals 10 minus the 1 will be 9 over 39. So k will be the ln of 9 over 39. So my equation, the logistic differential equation, if we're solving it, would be P of T. So this is our final answer here, equals our C, 2,000, divided by 1 plus our D, which in this case is 39, e to the, well, whatever that ln of 9 over 39 is. So ln of 9 divided by 39, negative 1.46. t. Now, we do have one more thing that we should do, and that is plug in what k is. Now, these two constants are not the same. The negative kc is what I let be k. So this equals my negative 1.466. So the actual k value in this equation would be this negative 1.466 divided by negative 2,000. So the k value here, to get the actual differential equation, is our negative 1.466. I'm going to use my answer button, divided by negative 2,000. So I get 7.33 times 10 to the negative 4. And that's my differential equation. This is my solved logistic differential equation. It's always growing fastest at 1,000. Now, if you want to figure out when, the time, we can take our equation now and set it equal to 1,000, and then we can solve for t. And you guys are usually pretty good at rearranging that equation. All right. So I'm going to jump down to the moose problem here. So skip one page, skip a problem. You can do that one on your own. And this is a little bit different. This is what you'll see it on the AP exam. So the first thing you have to realize is this is logistic growth. It does tell you it's logistic differential equation. And this is in that second or the third form that I showed you, where this is our C. Okay, if you want to put it in the other form, you're going to have to factor out a 1 over 200 times 0.06 m. If I do that, if I'm dividing by 1 over 200, that really makes 200 minus m. So these two equations would be the same thing. So it's telling me the carrying capacity is 200. Now, it does tell you that m of 0 equals 50. Okay, that's lovely. I don't really care. What it does ask me for is the limit of m of t. So it's actually looking for the end, like what does the moose population tend to. Now, technically, if I had a negative moose population, I would tend to 0, because that differential equation, the way it looks, you know, like we get this to be here. But anytime that we're above 0, or we're above our carrying capacity, it will tend to our carrying capacity of, in this case, 200. So the answer to this question is just 200. That's it. That's what it's looking for, is where does this get to? All right, let me see, is there anything else that this asks us as far as those go? So that's the end. So the big thing I want you to kind of notice about this is they do it in multiple choice. I've never seen, no, I take that back. You can see this on a FRQ. That is a definite possibility. But it's noticing what this formula tells you, okay? Where the carrying capacity is in the formula, and what that carrying capacity means about the population as time goes to infinity. Okay? So the book problems don't matter quite as much as the AP problems do. You do have to know the population formula, this guy, that's C over 1 plus DE to the KCT. Like, you do need to know that. But you needed that more for our chapter and not necessarily as much for the AP exam. Okay? All right. Have a good one.